So I'm going to talk of things, things which you are very familiar with, because Anurag Kaushal, I think, has already summarized this type of work a little while ago. So, but anyway, to make it accessible to a broader audience, I thought I'll just very briefly summarize the SYK model. So as you all know, it's a model of n real fermions interacting in groups of 4 or more. In this talk about groups of 4. The groups of higher numbers are interesting and just work in that direction. And this model degrees of freedom are very simple. They are real fermions, satisfy this commutation relation. So basically, these are gamma matrices. And the dimension of the Hilbert space of this theory is very easy to count. It's exponentially large to the power of 1, 2. This is the Hamiltonian, and this is a random coupling, which is distributed by this sort of simple Gaussian measure. It's all very well known. I'll just very quickly go through it. So there exists, the important points here are the following. We're interested in large N and large J, basically because we can do some analytic calculations in this lesson. On the other hand, this model can be run on a computer, and one can really study a lot using numerical methods. Many people have done. But large N and large J, we recognize that there is a infrared fixed point in this theory, and which has an emergent time reparameterization symmetry. The low energy degrees of freedom are these maps from time. Some function of time with power 1. This is with S1. And you have to mod out by SL2R, and this is the main culprit, and all the difficulty of solving this model. Justin. So you are late.
Very sorry.
Yeah.
I know it was 10 o'clock.
I'm sorry that it's at 10. I apologize. Okay. So there's a degrees of freedom, and this is the effective action. So Schwartzian, these are the low energy degrees of freedom. Now, important results with this subject, in my view, this is number 4 is perhaps the most important. Tells you that the density of states is given by this very simple formula, but with this very important exponent outside. So it tells you that a small interval, there are exponentially large number of energy levels, spaced small, e to the minus 1n. And I think this is the only model or the only dimension in which we know this type of explicit formula. And I think, if you ask me, we need to really calculate this type of thing in higher dimensions. What is the spectrum of it? We know that. Where is the information paradox? It's like a heap of matters. You know the spectrum. Everything.
Sorry, Spenta, just to say here, this shows it's not a unitary here.
Yes.
So, if just the information puzzles is usually stated by saying you have a unitary time limit.
So you're wondering about this Hamiltonian having a random coupling.
Yeah.
Okay. So my response to that is the following: that just take one copy of this. Just take one sample and calculate the theory. That's a unitary theory. So if you are powerful enough on a computer, you'll be able to really do this. And I believe that you will be able to, reproduce formulas like this, especially this.
But you can't get this formula. You will get an approximate. This will be an approximate.
I know because it comes from here, and this cannot be written as a standard density of states. But fuzz it out a little bit. These days, I want to just think very numerically in the sense that, there is some big computer that can do this job, and we are trying to sort of train it with it. But the important point is that this you will get this far always, and that is the point. I appreciate it.
No, since we have the chance of
So unitary. it's important that for example, the way I think about it is that the 4-point function is calculated in this theory by Stanford and Maldacena. So if you look at the 4-point function, you get a spectrum of states basically. Here the conformed. That spectrum of states actually is very correct. It's positive. It's gapped. And there's this huge underlying low-lying levels, which we are trying to approximate by a continuum theory. So in that sense, I don't have a problem actually.
That's true. What I was saying was, in a sense, the information puzzle is that you have, at first approximation, this kind of post-grade smooth density of states. But the actual, if you had a unitary Hamiltonian, would be discrete levels. And how do you see the effects, the discrete, if you're leaving approximation?
So it's like, how do you glean from effective field theory? This is effective field theory of this theory. How do you find out something about the microstates? This is, in a sense, the type of thing I'll be talking about. Okay, so fine. Now, that was about the SYK model. Now, the dual theory of gravity. We know the degrees of freedom, metric, dilettone, and the dimension reduction. This people, including Sandeep, collaborated studied. Dilettone basically is the avatar of history. There are other two-dimensional theory of gravity which we had studied using the method of coefficient weights. Both of these theories, the low-lying degrees of freedom are identical to this SYK. That is why this stuff is called interesting. And there is a formula then given if you solve the dynamics of the function therefore T. There's a formula for the metric gravity.
Sorry, just to understand this.
Yeah.
Volume of gravity is slightly it's not the same as
No, not at all.
Is there a random matrix theory?
That I don't know. But if you look at the near the infrared point,
Then you get the difference.
you get the methods of joint orbits, then you naturally get Satashvili and Alex. The theory of gravity, which is highly non-local, can make it local, it will look like Liouville theory. But that's what comes out, and it's the large gauge transmissions there also, which give rise to the Schwarzschild. So in a sense, but I think JT gravity is more important because it is a dimensional reduction of a higher dimensional theory. As you know, this very beautiful work of Riachi and Yesu, they have used this theory, actually, dynamical theory, to make statements about four-dimensional black hole, which is highly non-trivial. That's
just I say in the work we did, we showed you can use JT gravity to make statements of scattering of potential. So in a sense, that connection.
I mean, the density of states actually works by this. Yeah, I'm sort of very fixed on computing the spectrum all the time. I don't know why, but it's my thing.
All right. Just one second. So, Unka, you wanted to say whether this Stanford Schenkers are kind of that matrix model, but that exists for yeah. So that isn't there, but it does have the quality of gravity. It comes from like conformal matter in which the matter is integrated out, and so there is that kind of a take also. But we didn't pursue on that.
All right. Okay, so these are some preliminaries about the gravity. So this is a formula. There's an explicit formula for the metric, which is nice. You can look at it as follows. Actually, either you use this formula with simple boundaries, or as Stanford Maldacena, basically kind of boundary of ADS2, approximate ADS2, and locally the space-time is ADS2. But these are just all not very important. So here is a solution which we call a black hole. In these models, the metric is just This is the Poincare branch. And if you look at the Euclidean solution, this is terminal radius. So I just go fast because I'm spending too much time on things which are very well known. All right, so these are other well-known things. So here is this diagram. And the important thing in this slide is the fact that this boundary over here is characterized by. Not at all. I'm sorry to be so early for other reasons of your institute. So so the boundary curve is parameterized by this function f of t. And this z is telling you that we are very near the bound. It's all pretty well known. And so basically we are looking at a theory of curves. And from the type of geometries which you sort of can come up with, we can describe a black hole spacetime or a non-black hole spacetime. The key point is that the vanishing of this Jacobian of this map, t going to f of t, is the key point actually. This is a point made very well by Kourkoulou and Maldacena that signals the appearance of a horizon in the bound. And if f dot t is positive, not zero, for all t, then the spacetime has no place. Okay. So this is also very well known. Kourkoulou and Maldacena found a perturbation of the SYK model in which you can resolve the model in perturbation theory so that the solution is always f dot positive and there's no horizon in the geometry. And this is the point that really attracted me to this. It's possible to, introduce an explicit operator. You can always say, okay, I pump in energy and, negative energy and the black hole goes away. But they found an explicit operator actually, which can do this job. And there is an explicit calculation that tells you that the metric has no horizon. So this is what they did. In a very static situation, very simple situation. And the operator is this one. These are the Majorana fermions. This operator, in the infrared dimension of the operator, is 1/2 because the fermions infrared dimension, 1/4 fermions. And these objects, SK, are just plus or minus 1, which are the eigenvalues of this spin type operator, because SK square is equal to 1 given the commutational relation. Okay, so
this operator is inserted at every time, constant.
It's in the Hamiltonian. Yes, certainly.
So usually you insert something at 0 to pull the boundaries together, make it traversal.
No, that's of course that's a story actually, but this is what I said. So there, of course, what happens is that you take two-sided model, right? And you take this Jefferies-Tau type of interaction between the two sides, right? Let's say the fermion here and fermion here, and couple it and resolve the system. So what you find essentially is that the important thing there is the Hamiltonian. Now the Hamiltonian with this interaction develops a gap in the spectrum. And this gap actually implies the existence of a new space-time, a wormhole. So in that sense, the black hole is also gone. So absolutely right. So this work of Kourkoulou and Maldacena is patterned on those ideas for sure. Yeah. So this is a one-sided problem. That is what we're on.
But sorry, yes, yeah, understand. If we didn't have this perturbation and we just took the SYK model, one copy, and we flow down to the infrared to get this strictly confirmed.
Yeah.
I thought that was describing just ADS2 without black.
Thermal ADS2 is the black.
Correct. But that's very in the Lorentzian also.
Yeah.
But in the Lorentzian, I thought it would just be ADS2 without any horizon.
No, explicitly
no, because there's no temperature then in the SYK. I'm doing the Lorentzian theory.
Yeah. So the way to answer this question is that I first do Euclidean, let's say, right? Then I make a analogy continuation. See, the temperature factor is here.
That's right. Then you will get it at finite. Yeah, I was saying, yeah, you just do the manipulations in Lorentzian space to begin with.
Yeah, you just have the Poincare patch, that's fine. Then there is no black hole.
Correct.
That's another space time. That's another solution. Certainly.
No, I just want to make sure I understand. If I start with this, so now when you turn the on this Maldacena, the point is that you get a geodesically complete space time. This is not like the Poincare horizon radius.
It is a.
And on the boundary, it would be able to tell, right, in terms of the Schwarzschild. As far as I can tell, I don't study the local amounts.
I mean, in the Maldacena paper, they consider the the geometry corresponding to the pure state. So each of these pure states were like microstate formal thing because that they're not like the ground state, and the punctual was the end of the world plane and a horizon. So the horizon corresponded to temperature, which was given by the temperature that is there in the pure state. So, and then what Spenta is saying here is that this perturbation, if you add this perturbation, then the horizon moves. Whether it moves away or not depends on the strength of this perturbation.
I see. Okay. Sorry. Thank you. So the general picture is that you have the horizon and the end of the world plane within.
So in a one-sided discussion, you need an end of the world plane because you need to project, in a sense, start with side the project. You get the end of the world plane. So this is the space-time.
And just as you change this perturbation, you move the location.
Yeah. So what you do is basically that there is a perturbation strength, and if the perturbation strength is greater or less than, let's say, 5 on beta j or something like that. The beta j is large in this model, but we are at low energies. You can stay within the black hole space-time or shift the horizon and can shift it away.
So Sandeep was asking whether you could sit at the boundary and know that there was a horizon or not. I thought, but I know very little about this, that it's a question of whether this regulated boundary curve goes and hits.
Exactly. Yes. So that's the x dot equal to 0.
Becomes infinitely accelerating.
Yes.
Then you will get error.
Yes.
So all I'm saying is, at least without this perturbation, I'm sure, to do the Lorentzian theory, you get the Poincare patch. Where you don't get errors.
Okay, yeah. But could you know that sitting on the boundary?
Yes, that's what I was saying.
That's all. So, yeah.
F of t equal to t.
Yeah. And the construction, just to add to what Spenta said, as you know, is you start with a given state here, then you evolve Euclidean space by beta by 2. And then you will go into the Lorentzian. You start with a very particular state, so smear it out by a Euclidean evolution of right, so okay, so that's why it's termed the Euclidean.
Yeah, so it's so Sandeep, we are starting with a state.
I'll explain all that. This was just
also remind everyone that Spenta are
What time?
Well, 12, 15. Hard is 12, 15, but soft cut off.
This.
I'm so sorry.
No, I could quickly ask you, the intuition is that actually this operator on that state removes energy, right? So, and can you just roughly explain why that's the case?
Yes, I will. I'll be getting to that. Yes, here I'll explain that too. Yeah, I'll explain.
It takes energy out, and so it's no longer that.
That's the one.
But you see, does that mean the end of the world plane becomes causal contact?
Oh, the end of the causal contact with the
asymptotic.
eventually, yes.
When you're not left with any horizon.
will it become parallel?
On the end of the world brain become parallel.
That's interesting.
I don't want to get into these type of questions. I'll tell you why. Because I will not be able to give my talk. I think that these questions are easy to answer. Okay, I'm sorry, but let me just continue. Okay, fine. So here is the point that a very important point in this subject is the fact that the you can actually arrive at this set of states called Vs, which are specified by these n quantum slots, in which S1 is plus or minus 1, S2 is plus or minus 1, etc. Okay. So these are the states of the SYK model. They are not eigenstates. They are in fact very high energy states in the SYK model, but they are exact. And it immediately tells you what the dimension of the inverse space is. Now what you do is you take this state and act upon it with a low energy projection on it, as we usually do, where 2L is basically the inverse temperature, and beta J is always good. So this is the proposal of a black hole microstate. But that's the point actually, that these people made this proposal that this is a black hole microstate. Now, it's a very fortunate thing. In how many models do we know explicit formula for a black hole microstate?
So you just want to say that's the spin basis. I will just want to this.
Yeah.
And then that's just the evolution by some length.
Euclidean evolution, yes, so that you project onto the low energy sector, very complicated state. This one is a very complicated state. L is very large. Okay, so
Pushed by beta by two.
yes,
You start on this side, you go to that.
exactly. That's okay. All right. Now, in the work of Kourkoulou and Maldacena, the state in which they worked matched the spins which I mentioned, the operator. You see, I was mentioning over here that these numbers, right? This operator. So if you match them, the state, these numbers are identical to the numbers that appear in the operator. So this is the state dependent operator, Kyriakos. Then you arrive at an effective Liouville type of theory with this new addition, and now you do some very simple type of thematics. And what is important is that with epsilon equal to 0, this function e to the phi is just a simple function like this. But with this object over here, epsilon appropriately adjusted, what you get essentially is a dip in the potential. That's the gap in the spectrum, which etc. Also, Maldacena, Chi, and all these people. But in this model, it's a very simple mechanical thing that you essentially get a potential that dips. So that's the gap. That is responsible for taking away the black hole. It's a simple mechanical model. So
we grow as you emphasize, going like fine hyperbolic routine. Sorry, instead of this big group of states that grow and that you emphasize.
Yeah.
Fine hyperbolic routine, going all the way down to equal to 0, you now get a gap.
That's the key point, dynamically. So, I mean, in terms of this potential picture, it is so simply beautiful, actually. And it's like this continuous spectrum. Now, when you do this fellow, what happens basically is that there is a thing like this. So this is the gap. It's such an elementary thing, after all, which is illustrated by this way of looking. Okay, so let me continue. I think I'm still talking about other people's work, so except the last time there's some work there. That let me now move. So let me just emphasize once more, or define a little bit better. This operator squares to 1. At large n, you have a ON symmetry of this model, right? I don't want to explain that. And these are precisely the subgroups of ON is 0, 0, 1 minus 1. So extra. And the operator which I mentioned is precisely this operator. And the important point is the computation of the diagonal element of this operator. I'm sorry, I wrote here, but it this fellow. So you compute it at large n, not low energies, but large n. This is an exact formula. This one. So there are corrections, but you forget about that. And this is the Green's function. So this Green's function has one leg in real time, another leg imaginary. So this is all you can compute. It'd be nice to actually calculate the matrix elements of that, which you have not been able to. At least I have not been able to. So never mind. We will not need that in this talk.
You can do matrix elements with different L's.
Right. Yeah. Now, now the important point here is this. I'll just state it that the contribution to low energy physics, that is when beta j is very large, is that this Green's function essentially becomes a function in terms of e to the phi of t. This is basically the following. I'm sorry, this is a parameterization of the function f of t.
Sorry, on the left-hand side of the equation, where is that in BSLT? Okay, sorry, left-hand side.
Yes.
This is O1 of t.
Sorry, early in the morning. No, sorry. Sorry. Yeah. So okay. So we are able to understand, and the important point here is that there's a dot product that comes here, which Kourkoulou and Maldacena basically said is equal to 1 because they chose the spin of the forming operator and they state to the same. It is not the spin. You can see something. So I think this is something. Okay. Similarly, you can take the square of this operator and so on. You can construct lots of operators now. Again, the low energy projection can be essentially given in terms of e to the pi, because it's square, so pi upon 2 times 2 is phi, so you get this. And essentially the point is basically that you have a whole family of operators which you can write down. And in this talk, I will not be talking about this full family, which we can discuss, might be an important thing to look at, but only the first 2 members of this family. That is let me just go ahead now. So as you see, every time I do this, I get these dot products of spin. All right. Oh, this is the proof, but I don't think we should worry about proofs. It's there in the slides. Okay, so now what is the model?
Now we have to understand where low is at. Because now it's acting on this state, if you choose S equal S prime, it's positive left. Yes. And therefore we choose the sign correct with
absolutely.
Yeah. Okay.
It's the sign.
Yeah.
Okay, good. Great. So now this is the model we study. We want to study evaporation. What I don't know. So boundary dynamics interacting with the bath. So there is. I don't want to use the word dissipation. I'll tell you why. It's to do that, but it's let's call it evaporation in this part. And what we found is the following: that you take this model of the bath, ordinary conformal field theory with NF flavors, so that the number of flavors is much, much less than the number of spins of the SYK model. And this is the interaction, which I will detail a little bit, with the model at the boundary. And this is the interaction which we choose to work with. And you might wonder how we arrived at it experimentally. Numerically, you try a lot of things, and the whole point of this talk is you try out things to get your results. What is the theory we don't know really the microscopic discussion over here very deeply. So you try out a lot of things, then you go back, and then you arrive at some reasonable answers. Numerics is very important. Also, Anurag Kaushal, amazing job. I'll explain that.
Sorry, this might be hard, but after you turn on the Maldacena deformation, say working and states, how fast do the autops grow?
How fast do
The outer time correlators grow?
I don't know.
The reason
I
I'm asking
understand what you're saying. Yeah.
Did you have chaos only after you smear it?
I understand what you're saying. Yeah, but
Just curious.
if you get to a state in which there is a gap, I don't think there is a growth of that. That's what I'm just intuitive, but I'm not calculating.
That's what I would have also thought. It's very odd.
So this we have not studied. However, we have studied how fast thermalization happens before you turn on this perturbation and after you turn on this. So it's you can see the emergence of a power law instead of the exponential decay in time. Yeah. See.
Nice. The power on the gaps.
Yeah.
Exponential in the time also.
Yes.
Coupling is only to a single scalar. So
No. So the coupling is to a sum of in scalars.
So I mean, you can choose the basis in which that's
You can choose a basis in which that is just one.
yeah. So okay, but those others will also play a role.
Yes. I mean, this is a very simple symmetric thing. So you may ask, why are we doing this? After all, if you want to study how, ordinary life, how things cool down, you just put things next to each other. The cooling process or the evaporation process is not very sensitive to the environment, right? If you take a cup of tea on the moon and over here, there'll be differences. There's no atmosphere there, but suppose we put some atmosphere there, and eventually, but the time scale will be different. Those are details actually. I don't know the answer to such questions. Why this really works?
You would need some large number of freedom to interact with the system or not.
Yeah. So the SYK model has large.
I mean, the CFD.
Yes. It's a two-dimensional theory.
Okay.
Interacting with a theory in 0 dimensions, right?
Yeah, also,
It's like the quantum model, basically.
Take enough flavors in a scaled proportional value.
So this is the picture. Yeah. It's very much like the Kondo type of model people study in solid state physics. You have electrons interacting with a heavy spin, or the older model is the model of pions and pions. Pions interact with heavy nucleon. It's the same model, it's the same class of degrees of freedom. The Kondo model is spin. The nuclear model is isos, but that came before. Okay, so this is the model where you just have the SYK model, let's say time t0, interacting with this bath, which is on this half plane, and this is the space-time picture. And I don't want to detail too much this end of the world brain business. Can read it in Kourkoulou Maldacena's paper or in our paper. Let me just go on. It's a little tricky. I just want to go on. Yeah.
Sorry, please do. Yes. Just to understand. So now we have the Maldacena Kourkoulou deformation turned on, but we do have a black hole, for example. Understand?
Yeah.
So we are at some energy, is it above the gap?
So Sandeep, the point is that the bath has an independent existence, before coming to t equal to 0. System there. It is only at time t equal to 0 that they start interacting. So before that, the initial state of the SYK model is the black hole state, this BSL which I know.
I see. No, but I was just a little confused because I thought in some cases you can pump enough energy away, so you're not left with the horizon, right? So I just wanted to share what our starting state here.
Yeah, so I will declare it now.
Yeah, I think the top half of your diagram is not the dynamic range. I mean, is not what you should. I mean, you know, the horizon in the top half is dynamic, so it changes actually.
Yeah. I understand. I mean,
probably you're just starting at the green line.
Yes, starting at the green.
Yeah.
After that, you are turning on the dynamic.
So the equations still very clear. So once again, this is just a very simple summary. Important, but I wrote it down. So naturally, we get a minus sign over here. And this is the coupling that we will work with in this discussion. And in our paper also, this is the one we work with. At low energies, it becomes this Liouville model with two types of operators. So this is a marginal operator and this relevant operator. In the sense of relevant and marginal, sense of merely interactive. All the others are irrelevant, which I'm dropping. But I'm not so sure that we should do that. But it's a different discussion. Okay. Now, so this is the model that we sort of work with. So this is the interaction part. This is the SYK part. So this comes from the Schwarzschild and the state. So this is the full low energy effective action we work.
So Maldacena and Kourkoulou turn on the operator without any finds, like with one.
Yes.
You are turning on only coupling to finds.
Yes.
There's no coefficient of the operator with a one.
Yeah, so our coupling is dynamical actually. So it's dynamical with a bath, basically. Right. And one thinks it's simple, but it turned out to be, you'll see what it does.
But if you have phi is equal to 0, then you just got the original back.
Absolutely. That's precisely what's described by this fellow.
Maldacena phi also had a coupling.
What did you say?
If phi I is equal to 0, you have the original Maldacena.
This one. Absolutely, this one, which is described by this action.
So the only deviation of the geometry from black is because of the matter.
Absolutely. That's the modeling we are doing. Yes, on.
Yeah, so we expect this approximation to take down at some cost.
So
Approximation.
That's an important, very important point. When we do the computation, you'll see. I'll come to that. Yeah,
sorry, but
don't be sorry.
It seems to me that you have S interaction and then you have SY, right?
Yes.
So if you don't, I mean, maybe this is what we're saying, but I'm just making sure if you don't have the external path, you don't have the Maldacena Kourkoulou model. You have SY.
Yes, you have SY. Yes.
Yeah.
So let me put it this way. What they did is put it for a constant.
Okay.
That was their model.
Okay, that's why it was their model.
That was their model. But of course, I mean, they didn't have two terms. But if you work with this, you cannot completely evaporate the black hole. You can't see that without a computation. So let me just. I think she has makes all this calculation. I'm going to show that.
If I might make one comment, is the if you integrate, So if you integrate out the paths, effectively it becomes like a dynamical coupling constant of the Maldacena.
Was that that's in the slides that come?
No, because coupling constant question.
No. Certainly. Nice. Free to. Okay, so this is the initial condition that we start with the density matrix with sort of squares to 1. So we have the density matrix of the SYK model, which is given by the BSL state, and we have the density matrix of the normal field theory, which is given by some sweet state. Yeah, I mean all that I don't know. Then we evolved the density matrix and we assume that nature is unitary. Actually, in this case, may not be unitary in an expanding universe.
So is it important that the CFT is not in the vacuum? Or can you just tell the CFT in its vacuum?
It is almost in the vacuum because, and I'll show you the states which I just want. So this is the state I'm working in. See. So if KL is very large, if L is very large, then it's more or less vacuum. So L behaves like the quote temperature unquote inverse.
Yeah. L is inside tangential outside that.
Inside. It's tangent hyperbolic of KL, I'm sorry.
Yeah, no, then I don't understand. Why does L large make it like that? Tangent goes to 1.
That's the ground state.
Right. So L is large means the temperature is very low. Very low temperature, you will just see the ground state. That's all. Nothing really.
So maybe just one. This capital L thing is the Euclidean evolution that is used in the conformal field theory pure state. So there's a pure state that we're using also in the conformal field theory.
Yeah, that's this one. That's this one.
Yeah, but since the capital L was not explained, so I'm just saying that if you take that Euclidean evolution to be infinitely long, then that effectively protects it to the ground state.
Yeah, that's one way of looking at it, but just think about it as a squeeze state. We all know about squeeze states from our quantum mechanics, Kosh KL, Sinch KL, etc. Okay, so now we have done our calculations very, very, very carefully. Just one minute. And this is the things I want to emphasize. We work with the conformity theory or this field theory bar with a finite cutoff in all the calculations and then take the cutoff to infinity. And these are the limits in terms of which we work. Yes, sir.
In this slide, you get the equation root square equal to rho over.
Yes. This equation.
Yeah.
Yeah.
Yeah, what is this mean?
It's a pure state.
Oh, it's just a pure state.
Root square equal to rho. Okay. And then I want to evolve that state. And also rho square equal to rho because it's unitary.
Yeah.
But then what I do is I trace out some things and I get an open system, etc. All right.
Sorry, yes, in that previous slide, just before little L again.
Little L is twice little L is eta from the SYK model. That's the so-called temperature parameter of the SYK model.
Oh, I see. Okay.
Yeah.
So you take the SYK state when you make it begin to interact at the corresponding temperature.
Yes.
Density matrix.
The temperature of the bath, or the word temperature is not good because we are working with, we are not really doing thermal physics. It's a it's a pure state with this parameter capital L, which acts like an inverse temperature for the quantum theory, and small L acts like a inverse temperature for the SYK model. But you see the way I introduce this is essentially into the state e to the minus L times SYK. Okay. Is that okay? Shall I proceed? Fine. So, okay. So now we have to grind out many things since we are talking of evolution of density matrix. So naturally, the path integral involves doubling of degrees of freedom, and this is the Schwinger-Keldysh path integral. Everybody knows that, right? Here. Okay. So what you do is you integrate out the conformal field theory of the inner scalar fields. You integrate it out. You can do it because it's free Gaussian. It is more complicated and strongly coupled. You can't do this. Can't do this. So then we can't do our work. So let's see. So and then
so far, I mean, NF minus 1 scalars did not play any role, right? You effectively coupled your system to a single scalar.
No, I couple my system to a sum of these scalars.
But that's a single scalar.
Yeah, that's a. But it contributes to NF, no?
No, why? I don't understand why.
No, of course it does. Because what I'm saying is that it's contributes. this is coupled to the SYK. So then I multiply and divide. I make NF is very large, so I do 1 upon NF. That's and then I do the trick that this is order 1 or small and do a saddle point method. So if you work with one flavor, it's probably very hard.
But that's what I don't understand. I mean, the way this coupling is written,
Yes.
it might as well have been a single scalar, right? Because I just changed the basis so that this starts looking like a single scalar. And the other n-1 scalar is free. Then I don't understand. That's like just putting nf in front, a big number in front.
No, I mean, this is a consistent approximation. If I have just one scalar field, suppose NF is equal to 1, okay? Then of course this part is not there. But I don't.
That's my worry also, because it looks like it's a single scalar field. And now if you just put NF in front of it,
So ultimately we have an n times some action plus NF times saddle. I want to do a saddle point method in large capital N.
yes.
Okay, because otherwise I don't know how to calculate that.
Yes.
There may be ways of doing it. And because of that, I pull out this in here and do classical physics of large N for this.
I agree that this is what you want to do.
Yeah, but this is what we did.
Can you?
Yeah.
Because still seems like it's coupling to a single scalar with an NF number in front. That can be absorbed.
You're saying that I can do single scalar, but just put that thing by hand.
Yeah, I mean, you can just absorb it. So NF doesn't really exist, right? So maybe I don't know.
When you integrate out scalar scales,
okay, so it's some sort of a two kind of limit.
See, if you integrate out the NF, then also you'll get an NF. So all those things I would like to collect and divide by capital N. It's systematic. That's it. It's just that. But if I just work with one scalar field, I cannot do saddle point method.
No, but as Omkar said, you could simply scale the coupling in a particular way so that you can pull out.
What about the integral over the scalar fields? The integral over the scalar fields.
That's Gaussian theory.
I know you can do it, but how do you do it? I want to raise that determinant to the power NF. So that it is NF times log of the determinant. And then I can do saddle pointing.
Yeah, I think you're right. I would agree with what Spenta is saying in the sense that I can't quite put it here, but say if you take the NF scalars and you couple them to gravity, 2D gravity, it's important to have the NF because it doesn't matter how you define fields. There's a canonically normalized stress tensor. That's field redefinition in there.
Yes.
And unless you have stress tensor worth a conformal field theory with central charge NF. You can't make it consistent classical. Speak of it.
You have two stress tensors.
All of them. What I'm trying to say is that you need the stress tensor of NF, that is NF C equal to 1 CFTs. Otherwise, you won't get a.
No, but I'm saying gravity sees only one of those, and the other is a
no, then I don't. The limits I know is that gravity sees the stress tensor. I mean, of a C equal to NF.
I agree. That's what you would like to.
No, but that's what. That's exactly what. That's being done, right?
This is. I don't know. Maybe I'm being stupid, but it looks like that's not happening, right?
It is happening.
Because, I mean, if you go back to the initial coupling definition, why can't I just choose a variable sigma for this sum? And the rest of the guys will just don't play any part of this coupling, right?
No, say that. But when you.
Because it's a quadratic theory, you can always change the basis.
But you cannot change the fact that the central charge of the conformal field theory is proportional to NF, which is large.
But it's
and both are interacting, you will need it to do a.
Both are meaning the
Scalar field is interacting.
Yeah, single scalar field is interacting with your.
No, not single scalar. I didn't say that. I put NS scalar field.
So this is, why can't I just define this to be sigma? Why can't I define this to be sigma?
It doesn't work.
Well, I mean, I can just define it this mathematical manipulation.
It doesn't work because there is a field theory actually. There's a field theory of not one scalar field but NS scalar fields. The degrees of freedom, you need to give degrees of freedom there also. Okay, we can discuss this later.
Okay, fine.
Unless we have something special, field by field kind of thing. The other way I did,
The CFT state.
the same thing. He's choosing some to work some particular state. And maybe he's doing that in a simple way, feeling outlier, which would not then be simple.
Yeah, very fine. But the dynamics would still.
Yeah, but he's working in a particular state. Maybe that's
The squeeze state.
the squeeze state.
What can you ask that states?
But it was with some squares, right?
You know, the fluctuation, the fluctuation. For the 2-point correlated fluctuation, we care about NF degrees. Okay.
No, my point is a very technical, simple point. How I can do a calculation. If you have one scalar field, I claim I cannot do this calculation. Why is that?
Is it part of it? But there's any part of scalar term.
Very important. Because I will divide by the four flavors by the colors and put that fixed in small. Then I can do a semi-classical method in large N. Otherwise, people have done this in QCD also. This is the Veneziano model.
So the way I was saying, why can't you? I don't know. I mean, you don't agree that this is effectively single scalar, but this coupling could also be. Let's say you do this for single scalar. Can you not scale the coupling so that this is fixed and all and comes out?
But then in your conformal field theory also you have just one scalar, na?
Yes.
So you're stuck with it. I mean,
What is the problem with that?
I can't solve by semi-classical method. That's the point. I mean, you're right. You can do what you want actually, but if your computational tool has to be such that you can solve that problem. I mean, I don't see there is any problem actually with various ways of doing these couplings. Personally, hopefully they all work, but I can't do semi-classical method in large N. That's my point. It's a simple point. Yeah. I mean, I'm not disagreeing with you, but then I ask you to take the next.
Oh,
Yeah. So in the state, what was that AI against? That was the annihilation. What? That was creation of breakdown. Yes. So now if we went to a state like this for your sum defeating, that would be sort of like sum over AIs over these squares. Right. It would not be the same as this.
Yeah, that's the yeah. In NF Gaussian random variables, which is different from one random variable. This is what Spenta really needs. If it's from the gravity side, I completely understand. This is something that no, I agree.
Yeah.
but it's only in the state, not in the dynamics.
So the state I think will be very.
Yes.
I will not present a calculation, but you'll have to put all those things, do all the integrals and arrive at this object. This is the Feynman Vernon influence functional. You integrate out the path. So now you work with the open one field theory, which everybody is familiar with. And you get this lot of
Hardly everybody is. Before this work, even I was not so much.
This is textbook material from Kamenetz. And where I sit, actually, open quantum systems are all over the place. That is the thing to do. You didn't go small. Anyway, yeah.
Does the fact that you're coming into fever, does that make the formalization time very large?
Yes, so that is the point actually, because I'm able to do it because it's a free path. you get saddled because of massless theory. So you get saddled with a very long range objects. As you will see, if the bath is very strongly coupled, it will not happen. But then I don't know how to do the computation analytically.
But you expect that?
Yeah.
Affect that normalization.
Absolutely, absolutely. How fast something evaporates. So which other parameters I should actually evolve? Can I discuss, most efficient evaporation of a black hole? There is where I was wanting to say that all these other operators actually might play a role. And you have a big control. It's like an engineering problem. There's a huge control space. And what you have to do actually to have most efficient evaporation of thermodynamics. This is the problem of theory of thermodynamics of small systems. It's a very beautiful thing, but we have not done any of those things. I just wanted to allude that very much.
Because once please. No, is that if you did the problem in the gravity side,
yes,
you had JT system.
Yeah.
Also, and you thought about entanglement,
yes,
how it comes back.
Yeah.
Also, you need infrared because for a massless data, yes, the entanglement also is higher. That just saying there's a parallel, but then the question of return is very insensitive. That's what in this whole get. So anyway, the parallel in your try to phrase for similar.
Anyway, later on we discuss about paper. I have a comment on that. Okay, so is that clear? I mean, this is very formal. This is Schwinger-Keldysh. Sorry, you want to say?
We can talk. No, you'll talk.
So I don't want to detail this. So basically, because you are looking at path integral density matrix, you have to go and come back because it evolves by a joint action of the evolution of and just do it, and you get this object actually. And all these kernels which we have over here were computed with finite cutoff and then let the cutoff. Okay, so then the effective action essentially is given by this double copy action in which the SYK model has two copies, phi and phi bar, Feynman Vernon function, etc. So I don't want to detail this. Now we have to do a very important trick which was discovered by Keldysh, that you take a linear combination of the copies, plus and minus. So this is all textbook material. I mean, there's nothing we have done. All well. Okay, so you do this, and now what you do is the following. There are two fields, phi c and phi t. So we do perturbation theory around phi equal to phi bar. That's one perturbation theory. I will not be discussing, but that's not the only saddle point. That perturbation theory you do in just by the standard method around phi q equal to 0. And the action that you get is following. I mean, you get this linear term. That is the whole point of Keldysh. You get a linear term which multiplies what would be the equation of motion if this term is not there. This is the fluctuation term. Okay, so these are the definitions. These are the kernels, and this is the very, very long range kernel, which depends on capital L. Capital L is the Barth parameter. All right. So everybody okay with this?
And the fluctuations are done by 1 over.
Yes, absolutely. Yeah, absolutely. So now we come to the central equation of our
square root, number of flavors of the expansion.
Number of flavors. I'm calling it
number of colors.
Okay. Yeah. Okay. So now what you do is, because you are doing quadratic, you do Gaussian. Rewrite this as another Gaussian integral, and you derive Langevin type equation. So this is a derivation of Langevin type equation. It's still can't usually just write it down. But here Schwinger-Keldysh method enables you to derive this equation. So this is a very central equation of our paper. This is the equation we will now try to solve. Okay. Right. So very important, just maybe a frivolous comment that the noise actually over correlator is Gaussian. It's given by this kernel, but it's also multiplied by the field itself. So this is called a colored stochastic differential equation. And most of the literature for these equations is found in people who work in finance. Something I found out actually as we studied all this, that is a guy in finance that use this type of models. It's a hint. I'd like to go and work in finance. 1 year. This is what science does. This is what we've done. Anyway, so just some words to explain this. Sorry, exactly. I don't lose the thread. This phi q was the difference field. Yeah. For the field phi you wrote here, or is no. So what happens? What happens is that for the Liouville field, there are two phis. I meant Liouville, this is Liouville. So we are working with then I'm with plus and Liouville minus, and phi q is plus minus. So both of them fluctuate. I've integrated out one fluctuation in perturbation theory to treat the other one completely now. So that's the point. And the complete theory of that phi c is given by this box. All right. So this is the type of problem we have to solve. And it's a very, very difficult problem, actually. So
non-local in time.
Non-local in time, the correlator is non-local in time. There's a memory term.
Right?
Yeah, also it's called a memory term.
Yeah.
And it remembers, it's not Markovian actually. And okay, great. So a lot of fun with all this stuff. Right? So we can rewrite this problem in terms of a third order differential equation. These are some mathematical things. You can rewrite this problem in terms of 3 first order equations, very complicated type. And it'd be nice. These are equations we work with in statistical research. So the important thing is to find the probability of.
So your final equations will be very similar in spirit to this Caldera-Legge.
Yeah, but much more complicated.
The big difference seems to me to be that you, instead of having a harmonic oscillator for your system, you have this label.
Yeah.
But other than that, the path itself is a bunch of harmonic oscillators.
Yeah, but in Caldera-Legge, the frequency is tuned.
Yeah.
That's different.
Yes, you've got a particular distribution of frequencies that will comes from a conformance. So the path seems to be like a special case of Caldera.
You can say whatever.
Yes.
I mean,
but the system is different.
Yeah, it's system.
Yeah, the Caldera-Legge coupling was the linear coupling. Here it is like, so Caldera-Legge coupling, right? So it was like, if X was the system part, then it's X times Yi.
Yeah.
So what we have here is more like e to the power X times Yi.
Right. So we could work in the variable e to the power phi. That would change the system around.
That would change the system around. And in fact, this the stuff that Spenta said, that this K prime of phi c, this colored stuff, that's very important, because what it does is to modulate the friction. The effective friction term, gets an exponential damping. That will come to that.
I see. So is it sort of like the coupling of the system to the bar goes decays at late time?
That's right.
I see.
That will come to wait a minute. Yeah, I'll come to that.
I have to say one thing, please. You began your talk very beautifully emphasizing about experiment. Right? But allow me to say, by the time you wrote it in the Liouville field and adopted a flat measure for the Liouville field, and you're not getting that same. No. I can tell you what's. It's not for the quotient field. It is only for group S1 that measure has.
You've triggered some failed.
I'm sorry about measure.
What I missed out writing, and this was the ultraviolet divergence enough. It's also emphasized Stanford little paper actually is very important. Precisely this form. The coordinating of the SL2R. How to get the measure in terms of Gaussian view.
Yeah.
Right?
Yeah.
But that's what I'm using.
But you're using a flat.
It is a flat measure.
I don't agree with
No,
that.
I'm sorry, I don't agree with you.
Okay. But can you derive standard?
Yes.
Sine hyperbolic square root of.
No,
Yes or no?
yes. That is
Because I don't think anyone can derive.
Yeah, that is correctly done in Stanford, which you take. So do you think that's
It's only done for if you had diff S1, then you would get a flat. But not diff S1 quotiented by SL2. And the quotienting is important.
it's all important, but there's a change of variable that's happened. Some people.
They have not shown it for diff S1 quotient. Okay, yeah, I could be wrong with this.
So we might.
At least not that Kaminsky, whatever.
That doesn't. That's why I can say. So then we did not say.
I'm sorry, please excuse me.
No, not at all. We can discuss this.
Yes,
We have deliberated so much on this point. Let me continue.
Please go
If you don't answer, are you saying that the Stanford Whittle measure is not everything?
I don't think the flat, you can't do at least any rigorous transformation, which starts with the measure of Stanford Whittle on diff S1 or SL2 and come to the flat measure for this. If you just have diff S1 without the quotienting by SL,
I said in the beginning, culprit lasers.
Yeah.
I'm aware of all this.
Yeah, of course you are. I know, but I'm just saying I don't know of a proof. If you know, I don't.
How you mean that F divided by F prime square, that measure of Stanford Whittle, that does not.
When restricted to diff S1, quotiented by another quotient. I don't think that.
We have discussed this quite a bit. There was a ultraviolet divergence which I didn't.
Okay.
But you didn't notice that. Okay.
Sorry, everyone.
All right. Okay. Okay. And now this is a fun slide, but let me move on to solve the problem. So now let me just the classical solution. So I do this expansion and I get a classical type of equation over here and a fluctuation equation. Okay. So this is now just grinding out. Note that there is a symmetry over here. 5 minus 5. Indeed, it is not there in the ultraviolet theory, but in the effective theory. All right.
So what was zeta? The zeta was the noise.
Yeah, zeta is
Vacuum.
this one.
Yeah.
Yeah. The fluctuation.
Fluctuations of.
So now we have that big stochastic complicated equation. We further simplify it by looking at 1 upon root and fluctuation. So the main big nonlinear equation is this one. This is actually a linear equation when you substitute the solution over here for zeta. Okay. So
Sorry, Spenta, what was eta?
sorry.
Eta.
Eta is the noise.
Eta, that comes from phi q.
Exactly. So if you, for example, want to consider higher order corrections in phi q, let's say not quadratic but cubic, etc. So the noise is not then Gaussian, it will be more complicated. This is what Lobnagan company have done in their modeling. This type, not these problems, but other problems, and so the noise is more complicated.
So eta should be thought as a forcing field for zeta.
Exactly, it fluctuates.
Right. There's fluctuations in phi c because there are fluctuations.
Exactly. So that's like in standard usually. Any other question? All right, so now we have to solve. You can't solve this analytically or anything very complicated. So what you do is you do it numerically. Now, the way to do it numerically is that you basically create a table of couplings G and G prime and learn to run the equation. And so this is just let me explain in words. This is the GG prime plane. G and G prime are the infrared couplings. Okay, now that we are in infrared, we are looking at this theory, infrared coupling. Now you find actually that outside of this region, the red and green region, the solution blows up. And I'll tell you what I mean by the solution blows up means quite something like this happens. You take values of G and G prime outside that region, this is what you get. The solution blows up. Let me finish the slides before you ask the question. So, so here is actual calculations. And there are many more points actually which have been calculated. The blue dots correspond to the values of G and G prime, where the solution blows up in the way I showed you. The red dots, those values of G and G prime are such that the solution, the black hole does not evaporate completely. And the green region, the green region, or the green dots are precisely the ones in which you have complete evaporation. Why? Don't know. This is the result. And sorry. In fact, what I would like to ask you guys, I mean, is there any intuition for the fact that the solution blows up beyond a certain range of parameters? I don't know. Is it because we are doing low energy dynamics? Is it because we have left out some terms? I don't. If I introduce more irrelevant operators of the Lewis theory, would I actually circumvent this problem? I don't know. This is the way we did this problem. Numerical. So blow up means you will feel what exactly is created. This is the you will feel is done. This is exactly put G and G prime to be these values and calculate. I didn't do all this. I cannot. So I'm not doing. And this is the graph. Here, look at this. And the temperature inverse, we are always choosing something like pi times 10 to the 3. Pi is because you have to cancel some on vibration, etc. So this is the large inverse temperature, and with these values, this is the solution, and the solution blows up. There's no intuition by us. In the geometry, sorry. If fire blows up, what does it mean? Does the boundary move? Accelerate and move away? It goes inside. And it's plus infinity, not minus, right? Plus infinity. Minus infinity was set up like first. Plus infinity. So solution blows up, energies, everything blows up. So I don't have a physical understanding of this, really, honestly. But the perturbation is too maybe violent, I don't know.
This is the thing that was very suppressed by the original potential. The original potential tried to suppress going to plus.
Yes.
And yet it doesn't. Okay. Yeah. That doesn't. Potential blew up at plus. Positive infinity with this perturbation.
With this perturbation, which was this one.
Yeah, but let me ignore the perturbation for a moment. Just the original potential in the Liouville action.
Yeah.
Didn't that blow up at plus infinity?
No, that's this one. Yeah.
At plus infinity blows up.
Yeah.
No, that's a potential. So
yeah.
What happened was that the phi behaved like a particle, which was like a scattering thing. So it's at infinite time, it was going towards minus.
But now it looks like it's little plus.
Yeah,
that's the place where the original potential looked like it was infinite.
Right. But the particles were not supposed to be there. This is the particle solution.
That's what I mean. I'm saying that it's so strange because it's going to an infinite potential.
Absolutely.
To confirm.
No, he's right. Actually, what he's saying is that potential was like this. But when you solve for the particle in this potential, you didn't get this solution. And the solution blows out.
It almost seems like the bath is pumping a huge amount of energy into this, right? Because otherwise you can't.
Yeah, so that is correct, actually, most probably. And the point is why? Why is this happening? And I don't understand completely why this.
Well, perhaps there was always a danger. Because your coupling to the path was also blowing up as 5 and 10.
Yeah. But wait a minute. There's a very important minus sign. Like this.
Right. No, independent of sign of coupling. I'm saying just the magnitude of that coupling is blowing up as 5 goes to 10. So you can imagine a self-consistent kernel. Right? It starts going to large thing, and then the path pumps more and more into it, so it keeps going. Clearly, those G's are small enough to.
G prime is always very large. Shiraz in this numerically.
So in the regime where G's are very small, clearly it should not happen. Right? Because this is a small perturbation and you cannot go to infinite. Yes. But you can imagine that there is a critical coupling which overwhelms, right? Because both of them are going the same way.
So if you see this block, there is some demarcations over here, beyond which the solution blows up.
Yeah.
And you're allowed to.
But on the other hand, not evaporating is also easy to understand maybe roughly.
Yeah.
Because if it's going towards minus infinity, then the coupling is also going to 0.
Yes. Yes.
So it has to evaporate.
That's very simple. That's the way it's simple case. But it's the full evaporation which is the complicated.
Yeah, that's somewhere. I think I agree with the dynamics. It's like that you have the slide on the dynamical potentials. Just time to identify the.
Just one thing. What is the signature of full evaporation?
F dot is never 0. F dot when you to the phi is always bounded. That's phi is always bound.
Phi is not going to minus.
Neither to minus nor to.
Okay, I got it.
No, plus is okay. Phi should not go to minus infinity, because if phi goes to minus infinity, then it hits this the boundary curve hits infinity.
But I thought if phi started going up the hill a lot and goes up to plus infinity, also you would have a break.
Absolutely.
So it stays somewhere, or order 1 or whatever, and that is the complete.
So that's right. So I think sorry.
Yes, I was just saying, Shiraz, when you said that because of this potential, the coupling that goes up, but this means that G prime should play a more important of a role, right? Because it's not the phi.
Yeah.
In fact,
This is more tolerant of G prime going larger than G larger.
so yeah. So let me just say the following. Actually, that if G prime is equal to 0, you don't get complete evaporation.
But you get blow up.
You get a blow up also.
So then I agree with the limits challenging present.
Just look at the axis where G prime is 0. Outside here, you have a blow up.
More tolerant of large.
Yeah, it's a very it's a spatula which needs to be squeezed. Yeah,
No, but I'm looking at those numbers also.
yeah.
What was the comment? That it's more tolerant of larger G prime.
See, what Shiraz was saying was that it's because of the coupling.
It should be more sensitive to each of the phi.
Yeah.
Is the sign important? I don't understand the sign.
The sign is very important. Without the sign, you don't get it. You don't get the solutions.
In the Newell potential was the potential.
So the sign, there's a reflection symmetry in sign there.
Yeah, there is a reflecting symmetry.
So G prime both going to minus symmetry.
In the Newell,
That you can see very easily from the effective action. Yeah, sorry.
the Newell potential wasn't e to the power 5 by 2 or e to the power 5.
5. Not 5 by 2. 5 by 2 was the Kourkoulou Maldacena.
And you're saying you need both. You need both for clearly from
Yes, this plot is like that. You need both to get to the green. Otherwise, you just have this one.
Just to understand, and the sign is relatively minus when you come to the correct green. Yeah.
Very delicate thing.
Yeah. So, okay, so we found some good reason that this is expectation value of certain operator plus the expectation value of a certain operator square. Natural thing to do, and that gives a minus sign. Luckily. So it's not put by hand in some sense in the algebra. So, okay. Shall I continue? Okay, so this is a central point of the paper, that there are solutions, and the green region corresponds to the fact that phi is bounded. So as Dr. was explaining, f dot is positive, and that in the dual geometry it means it goes. On the other hand, in the red region, which is much more prevalent in the green region, you essentially have an asymptotic formula for phi as minus some constant, which is just the inverse temperature of the new black hole. Right. And yeah, okay, so the fact that this boundary goes as 1 upon square root of beta j, and this blows up like square root of beta, is all numerically motivated. There is no analytic handle. Only analytic handle is around here. This is very useful. What I'm trying to emphasize is that somehow computer-aided science is very useful. Just in pencil and paper may not solve hard problems. And now in that
Spenta is a new fan of numerics.
Very late in life, but John can't late life.
So could I ask, is the effective potential like the square of the company? I mean, the change in the modified effective potential, is there a square involved?
Yes.
Of this?
Yes. If you look at the, if you look at the, for example, it's all over actually. It comes from the.
Yeah, you said complete a square of this.
So it's always f times f prime or things like that.
Yeah. So could I ask, if you just change your coupling to alpha e to the power beta phi, and if beta was less than half, if what I'm saying is right, if beta is less than half, you should never see an incident. Do you know if that's true?
Sorry, say it again. Go.
Show me. Take your field and couple to e to the power beta phi to whatever to your sample. Just by hand. Yeah. Now, if beta is less than 2, or even some of such things, but if all beta is less than half, if what I'm saying is right, it should never go.
Yeah, I agree.
Is that right? Do you know?
I think it's right. Intuitively, it is right. Yes.
I see. So your Shiraz's point is it will appear squared, but anyway, there is a zeroth order coupling which is e to the power phi. That's what wins the
it can never go far.
So if beta equal to 0 is the order line case, right?
It's on the boundary.
Yeah.
So there it could happen. It could be a matter of how large.
It's a little bit less.
Yeah. A little bit less, right?
1/3.
Yeah.
Yeah. But also the fact that there is a crossover over here, which you can explicitly see in these are actual calculations. This is a cartoon. So there is also, I don't understand all these things.
There is something which seems very strange, which is from the gravity side, the complete evaporation is the most natural thing, right? The moment you turn on Hawking evaporation and the quanta have an infinite volume to go into, black holes may be evaporated eventually. Here, somehow it seems very delicate because from what you all are saying, either you run the risk of climbing all the way up, or you will just turn back gently and go after minus infinity. The model of radiation of Hawking, which is 2 dimensions. There are habitable degrees of freedom. There are light degrees of freedom on either side of the horizon. There is no picture here, and these are ellipse scalars. See, if you just do semi-class gravity here, the black hole color you ellipse scale, and you just solve the equations in the semi-classical approximation, you get complete black hole. Hope that. No, we should. For sure, by in the thesis of Sully. Just like JT gravity.
JT gravity.
Yeah, sorry.
JT gravity. Yes, I mean, but
we are trying to have a kind of version of that. I understand. I mean, so I mean, all I'm saying is the details obviously can be very different. But there's something about how we map defining the problem that is the most natural endpoint on the gravity side that is coupling between the hole and the black hole.
It's very sensitive to what's going on in the black.
yes.
Yes. And so in the place where it's not evaporating, what's happening is the coupling is switching. It couples for a little time and then switches off. That's fine.
Because you run out.
Yeah, because you're going to minus.
Because e to the minus 80. Right.
Can we, all I was asking was, can we have a coupling which is sort of more naturally mimic
Just like a bar field stream and out.
extreme?
I think that
How do we make it go back out? The point is some reflect. We are doing open points.
We have integrated the bathhouse. Many of these questions I'll come to the are very important, but we don't know about this.
Could you, sorry, please.
I don't see sorry.
Could you just, yeah, no, just of the scale.
yeah. So in JD, I would certainly have that.
Yeah. Although there it's more subtle because the correct boundary conditions are that the stress tensor isn't lower.
No, my point in all this discussion is that fine. So any coupling would have done it. And why is it happening that there is this type of detailed structure? Why is it that the solution is blowing up beyond the point? Due to good reasons, can imagine. Why is it that there's a green region and a black red? These are details of dynamics. I think just by looking at things, you cannot figure this out. I mean, this I cannot.
Yeah.
So I mean, these are details.
The unusual thing you're having is coupling to the bar is very particular.
Exactly. And the motivation comes from the fact that the work of fluid pulse.
Yeah.
Yeah.
Which is that, you try to set up a black hole problem. And you may just say the black hole absorbs it.
Yeah.
And then it'll just grow and grow. Sort of, I feel roughly a huge caricature, but of the thing just going. Or you can just say, I'm going to have a fire. And then anything that comes in reflects. And then it'll just reflect out. But the subtlety, in a sense, from the gravity side is that you have a smooth horizon. And yet, the information comes out. Okay, at least it's the first step.
The other thing is that we do not understand the bulk of formalism. It's not any obvious massless particle or massive particle. No, it's most likely some sort of a Coulomb field type of thing.
And firstly, it's state dependent.
State dependent. Yes.
It's not the center of the you were saying. So it's not. So you were saying
World brain, this operator is not the end.
the operator as such. Yeah.
So those are things which you don't understand completely. So shall I?
By the way, we have released the state dependence thing because we are using a different spin, a different operator than in the state.
You're going to need your exploratory near to it. So, but if you didn't know what the state is, what would that statement even be?
Yeah.
It's very far away.
I mean, in the sense that if you do a survey, you will get zero result for some. So if you didn't know, you can guess by your
look, I do it all actually. Yeah. It's exponentially like that. Yeah.
Not expensive.
or what actually you get.
Not exponentially. I keep spinning, but I will go.
Yeah. So we'll
Okay.
Cos theta is absorbed in G.
Yes, that is the point. So this is there is an ultraviolet coupling, right? Which is just let me write like this: G hat times, let's say, rope space. This the infrared becomes G, and this is basically
Yeah.
So in the infrared, you cannot see the difference between these two leaves.
Maybe. Microstate.
Share your wisdom, man.
I was speculating that maybe something what some people say was more essentially correct. That that somehow what you're coupling to is not local degrees of freedom near the path, but something more inside.
Yes, yes.
And that's why that coupling can so easily switch off. Because it's somehow the operator, despite Gautam's objections, it somehow knows about the microstate of the black hole, which is some insight.
Yeah. It knows by a scalar product. I mean, it's a huge high dimensional space, and black hole microstate is some spin in that huge space. Now, what we are essentially doing is that we have these probe spins. Coupling to the path is not with that spin, but with something else. So the cosine theta, essentially are there also.
Yeah. And you'll have this cosine theta sort of to the power n.
Yes. In general, that's right.
Right.
Over here, only square.
Why?
Because we are looking at O1 plus O1 square only. So S dot S prime and S dot S prime square.
Right.
That's what you do.
No, but I mean, S and S prime reaches an n-dimensional or n by 2 dimensional.
Yeah.
But if you have each theta
and
angular, let's say we take the modular set, then that would be cosine theta to the power n or n by 2.
No. So what we do is
But there are n sections.
Yeah, what we do is that we do this calculation so many times. So you do have cosine theta 1, cosine theta 2,
and a product of them, right?
all of them
Yeah.
there. And you after you do that, you may be able to infer the original spin, and this is what I will allude to. Allude to means not go into great detail, but explain.
Let's suppose all thetas were equal for a moment. Then we have 1 minus theta square by 2 to the power n. And now we use the formula that, the formula that gives you E. Okay, so we'll make this very small. So this is basically e to the power minus n theta square by 2.
Yes, I understand.
So if you start deviating even a little bit, the coupling just goes away.
Yeah, absolutely correct.
Because of the n. That's good.
So maybe that's the reason
So
why.
very tuned. They don't have anything to happen.
Very tuned.
Exponential, right?
So this is why the green regions are very small. This problem.
Just to ask you, I feel I've not understood something. You're starting the system to interact in I thought the black holes, there is a sum over microns. Or were you starting with one
micron is smearing. Smear by 1 minus beta.
One micron. Okay, and that smearing doesn't roughly give you a sum over all microns. Please. Because
No, you should, look, it is true what you're saying that really work out now. The exponential minus L. Really work it out all the products. All of them makes up. Certainly. But the way I'm doing it, the low energy formalism, this formula is beautifully simple. That this expectation value, which is Green's function times the scalar product of S and S prime. The Green's function low energy limit can be calculated in this form, and that gives you this limit fact.
See, this will be an overcomplete basis for states of unity.
Right.
I think that's what this. Right? Because then this will not be a complete basis, will be all. Still there is information.
There's information, but if the evolution by e to the minus beta s spreads out the states enough, you might have thought that it becomes more like an average over all the microstates. So at least some dependence goes away.
We see that. We solve it. Okay, and we choose the operator to have the S primes equal to S. You get 1s. You choose the operator to have S the little from S. You get completely different.
So are we saying that in large dimension, the radius, the volume of the sphere will be R to the N, right? So that's why in order to get a non-zero inner product, you really have to tune very hard. Otherwise, generically, you will just get a vanishing inner product.
That's
So very easily can estimate. Right? It's exponential.
It's R to the N,
Sorry, so there's the operator you start with, and then you want to get the, and then the other operator is what you come to the.
Yeah.
Then it seems somehow.
It's very sensitive. That angle between these two operators is very sensitive.
But this just means that this picture is a big picture. Right? I mean, this you'll still see a tiny coupling constant. I mean, a tiny cos theta. This G's you have to coupling, these couplings you have to take apart.
So the G's and the G primes hide and theta and cos theta.
But just to address Sandeep's point about whether the final answer no is which microstate is very interesting.
This F operator. Is there a way? I mean, which operator this one? Yeah. So over there, what I'm sort of very vaguely grounding for is if the black hole is smeared over all microstates, then the coupling we want to provide to the heat path should also be smeared over all microstates.
To make a couple more.
Yeah. And then that might be a better model. That's what I'm really. How would you write that? I'm not sure. You know better. Can you smear this F? By smear in the sense that it has some dependence on your spin.
I can actually do that. I mean, I can write down a very, allowed complicated operator which will involve higher powers of E⁵. And it overspills. And you can do that.
But just one thing that mitigates against that is that Maldacena Kourkoulou were able to reach exactly that state was what your university had said. And yet with this operator, they were able to extend it. Right now, it has to be, the operator has to be very finely tuned to your actual state. You will take energy out of it.
Absolutely.
And this operator did. So it seems like it's doing something without any experience associated with this. Saying it vaguely, but you hit a black hole normally, you pump energy. It will take energy out.
What I was surprised is that if you simply took their operator, there is no complete evaporation. I mean, that's a calculation.
Yeah, that's why I was
Yeah.
So one more analysis is going. Classical limit we can understand first, which is just to if you classically took the n scalar fields interacting with the black hole, just you don't have, of course, Hawking evaporation. The black hole mass only comes, right? Now you turn on the quantum effects, and now the black hole generically always evaporates. Now, is there possibly a way to take some kind of classical limit of the system? Then we could see whether it's first sucking energy, All right, so zeroth order is like a black hole, and now just asking.
I'm still perplexed about the result in the sense that whatever you say is, if it is generic, it should apply to large varieties of coupling. That is not happening. There is something about this set of equations which is quite complicated, actually, which I'm not able to.
You want to know the classical analog, what classically this coupling constitutes?
Yeah. But this classically, in the sense, we are doing classical physics at large end.
But I think something wants in the market.
But see.
What does it do? I replace SYK by geometry. And what is this?
Very good question. So that's so you need to actually then learn how to evaluate Bath correlators, which can be done. It's difficult. Or integrate out the SYK model, which is very hard. But numerically, you can do all these things. You see, you can introduce fermions coupled to Bath fermions or whatever. People have done this. So Chi and collaborators have done this. Also, Maldacena and Michelin have coupled two black holes, but they don't have a geometric understanding because they are not at low energies and are not working with geometric variables like f of t, which means essentially metric in the anti-gravity. And as we talked to a lot of people, actually, especially one of them was very keen. You must be able to describe black hole evaporation, this type of model. Can you imagine?
This person's name starts with M.
Last name with M. Some felt natural. No, I mean, you'll see how many natural things he thought. Okay, so shall I just proceed? These are the actual calculations, and this is the blow-up solution. And now let me look at the solution in the red region. So here I have written a slightly simplified version of it, in which I have put this G prime equal to 0, but if G prime is not 0 also, there is an augmentation to this term. Basically, this is the formula. Actually, phi essentially goes to minus infinity, where A is, A is very much like an inverse temperature. Not very much, it is the inverse temperature of the smaller black hole. And this is a solution like this in the red region. With G and G prime also, this more or less the characteristic is the same. Okay. So now let us come to the more interesting part of Volta. What is the solution in the green region? So this is very good. Firstly, it's difficult to access it analytically. So you got, but numerically you can find
a solution in the green region on top of the title of the space.
Oh, sorry. Green region. Black holes. I mean, no black hole. No black hole. Yeah.
Evaporates.
Yeah. So this is a solution with highly oscillatory around a certain particular value of the field. Okay, so this. Then once numerics tells you that there is a solution from here to here like that, you can analyze this analytically. And this you can do. So you can do perturbation theory around the 0 of f prime, and essentially you get a situation which is A functions. Solution. Stokes, it's called the Stokes equation in the literature. Which has a time-dependent frequency, and I will come to this formula a bit later. So why have I neglected psi square? So again, from the numerical analysis, which tells you that the solution goes like that. There is no other reason for me to say that psi square term doesn't function. There is no parametric smallness here, just for numerics.
Sorry, Spenta, this is the solution. Should you read it of whether Liouville field is neither going off to plus or minus.
Exactly. The Liouville field is hanging around, right, in a bounded region, but it's oscillating. Now, don't understand why, but I asked Juan Maldacena. He said it's natural, like, that you will expect all these oscillations, fluctuations. And I asked Lugnaigam, and he said, think about a drop of water evaporating. Not exactly the same situation, but as it starts evaporating, the end point of evaporation will have large fluctuations because the droplet becomes smaller and smaller and smaller. So perhaps there is some intuition like that to have this type of oscillations. This type of physics actually might be also there for higher dimensions, and you could never actually imagine this type of thing without.
It's like a boundary graviton test.
Yes. It's boundary. This is only boundary gravity.
I mean, because now you've got sort of like pure ADS rather than a black hole. You've got a boundary graviton kind of degree of freedom, and it's exciting at the end. That's how I'm thinking.
Yes. But do you understand this violent oscillation? I'm going to cut it off by time-dependent coupling. So.
I see we can take GT gravity and have some kind of boundary conditions.
Yeah, we have used all that in our.
The field will still fluctuate, the gravity field. Because it'll take the kick, it won't absorb the energy.
Yeah. Do you understand why such a oscillation?
What is setting the frequency?
Yes, so here.
Is it like oscillation in this effective potential?
I'll come to that. Exactly. So what is happening basically is that this fellow at time t equal to 0 dynamically, I don't have that figure here, dynamically, asymptotically becomes
This kind, right?
this kind.
And then it just oscillates around the wheel, right?
You see that Brownian motion, right? It is for me, but it's a way it's which omega square is that's frequency.
Yeah, frequency.
So then it's not stuck. So it is the time.
It is the time. So so that I'm coming to that. Right?
It feels very much like a graviton and ADS file. A global ADS file, you've got a graviton. It oscillates with some frequency set by ADS. That's what it feels like. Except that this is all.
But here it's like we're timing the frequency.
Time, is that right? Then is this potential changing with time?
Yes. So what happened? I didn't know where to put a cut on this talk, but what is happening basically is that you start like this, and slowly you become like this, and like this.
But what's the long-term behavior of that potential?
Like this.
Like this. So then the infinite time should go to a particular frequency.
Yes. So I'll come to that now.
Yeah.
I'll come to that. So this frequency is actually increasing. Right? Now there is a problem with that because it violates the low energy approximation. So what do you do? So this is a solution of course. This is also a solution as it goes along discuss. But we need this omega to be much less than 1 in units of J. Now I told you, we are in low energy approximation. Omega must be much less than J. So this means basically that there is some sort of time beyond which we cannot go in the low energy approximation. I just cannot be. And therefore there is some maximum time in which you should work, which is much less than this T star. And how to achieve that now? To achieve that, what you do is you slowly start decoupling the bath from the Schwinger model. And one recipe, which is supported by all the algebra that is there, that it should be taken as a square root. Just like this diagram over here, and the same with T prime. And now so this is what we call the quench protocol. So the coupling constant in the bath is now time dependent to rescue your low energy approximation. So we know just do what rescues your model. Maybe a deep reason for this. And then there is a maximum time at which the system stabilizes. Final potential is like this. And then you have this Maldacena Kourkoulou type of model. And there, the oscillation equation is now very nice because the frequency given by its fixed value, as Shiraj was saying, around here. And you resolve the problem. And this is the answer with the equation. All right, so this is the physics of the situation in which G and G prime, the couplings are in the green region. It leads to a bounded Liouville field, and the bounded Liouville field tells you that there is no horizon. That's the point. So this is the dynamical realization of Kourkoulou-Maldacena's work, but much more complicated, and only if you use their operator, it doesn't work. Let me just go on. So this is the summary. I mean, all the details are there in this paper, but it's just the summary. So this is the Euclidean theory, which basically wrote as rho time t equals 0. For the XYK model, this is the small L circle. On field theory is the capital L, the standard thing. So when you evolve the system, so this is the answer. The answer in the red region is precisely given by those boundary gravitons, which end over here. And in the case of the green region, the boundary curve essentially goes like this. And F dot is never 0. F dot. So this is the sort of final conclusion of a dynamical model like this. black hole coupled to the environment. Now, I don't know whether to call it evaporation. Certainly, it is not dissipation. It is not a dissipative problem. I'll tell you why. Okay, so then we computed fluctuations, the Brownian motion around this classical solution. You can do that. And in the case of the red region, where you have a smaller black hole as a final state, you essentially get this correlation. And it is consistent with the Einstein-Smoluchowski formula in which there is a linear growth, the diffusion. This is the diffusion. So, it's fun, nice. And the temperature of the bath also makes the diffusion constant, as it does. Okay. But for the green region, where you have no black hole, where you have this situation, again, the fluctuation is very oscillatory. So in a sense, it's like in a box. So if you, for example, the problem of Brownian motion, a harmonic oscillator Brownian motion in a box is exactly soluble. So we know that solution. You plotted it look exactly like this. So these equations are much more complicated. This is done numerically, but the harmonic oscillator, stochastic harmonic oscillator in a harmonic potential is exactly like this. The important thing is that if you, for example, plot the, so here you don't have this linear growth in time. That's important. Linear growth in time and the diffusion constant, which goes as the temperature in standard Brownian motion doesn't happen. This is more complicated problem. Right? That's what it is. Any idea why?
Sorry, what was the question? Sorry.
Question is that in the previous slides, I explained that if you are doing fluctuations around the small black hole final state, you get this answer. Okay, it's not very difficult to derive. What is important about this answer? It's the linear growth and the coefficient here. Yeah, exactly. And the diffusion constant essentially goes as 1 upon capital L. This you have seen. Because diffusion is proportional to temperature.
Zeta was deviation in phi.
Exactly. Okay, so this is standard Brownian motion type.
This laminated by potential modulated by.
Okay, that's there.
But this is small time, right? Continue forever. Oh, exponential, right? Definitely. Yeah,
Exponential.
Yeah. Okay, thank you.
So, but this is the point actually. The diffusion constant is proportional to temperature.
Yeah.
That fact doesn't happen when you compute fixed time. See, if you compute the fixed time correlator in the second case, that the black hole is not there, then you get this type of graph. So, it varies with temperature.
It varies. Sorry, the difference is what?
Let's see. Previously, the diffusion. If you look at the point correlator over here, this object is proportional to temperature. So it will grow linearly with temperature.
Okay.
That doesn't happen actually in the more complicated case. Even though the characteristic of the solution is very similar to harmonic oscillator with a stochastic. So if you ever take harmonic oscillator, Brownian motion, you can solve this problem.
Yes.
It's not very difficult. Okay, fine. So these are the differences in over temperature, the 2.4 relatives. Yes. No, for harmonic oscillator it will grow. That's what I'm saying. That
Here it is not.
This characteristic is similar.
Is but not nature is good. Okay, sorry.
Okay. So the next small thing is that this equation, classical equation, is actually a Hamiltonian system, even though it's very complicated. And so we can actually introduce the notion of a time-independent energy. So this is from where the equations of motion can be derived by just Hamilton's equations. And you can also plot this for example. You can see the energy and all this goes away.
In the case with the black hole.
So, okay. So this is one part of the talk that's sort of done. Is there any questions before I go? Shall I continue? Yeah. All right. So now there was this issue of how to infer the initial statement. So this is some thoughts about that. So let me give a very simple example of this type of idea. The actual case, it's not complicated. Because in the actual case, the coupling is not only this one, but it's also this also is there. So I'm presently putting G prime equal to 0 just to make a point. Okay. So suppose you have this type of system and we are given this type of ultraviolet data. I tell you what S1 is.
So is the mechanics ask one
Sure.
question. Suppose we put a infrared cutoff on the field phi. Do you think some of these results
Capital L is like that.
because that's for the I thought
Capital L.
yeah. Was that for the trouble is we have two phis. So let me replace
Phi or
chota phi.
Chota phi.
If on chota phi you put a infrared cutoff, then you can't exceed this value at that end, left end. We will attain some of the results.
But we are, the whole formalism is chota phi is fluctuating very fast on the scale of beta G.
If not fluctuating. So I was saying, even in a coherent slow way, suppose we don't allow it to go past a certain value. Will some of these results change? I'll tell you why I'm asking. Forgive me. But, with a standard flat measure on the UV field, if you put it in a box, the system is definitely got a discrete spectrum and a nice unitary handle. And so now you couple that theory to your big phis and okay, they can interact and all that. But as far as unitary evolution, the system is stable. And I was just wondering whether, so here, now if you lift that infrared cutoff from UV field, then okay, you may say, all right, it's a little ill-defined. Maybe you are mimicking in some way, some kind of continuous. So I was just wondering whether here you see something different.
I understand your point actually that the Schwarzian path integral was computed exactly gives an answer which is not Hamiltonian in nature.
Yeah.
And you would like to have that answer to be Hamiltonian in nature by just putting an infrared box, discrete levels. I don't know which how it will affect. My guess is that it won't change very much. I somehow feel that this continuum that is there of energy levels because of the variable potential renders is not in the sense of standard movement. May not be that important. Because it's very fine energy levels. You need to do that infrared in such a way the energy level difference is e to the minus n.
That's right. Yeah,
Not
that's
easy.
right. But till you don't do it, allow me to say, till you don't do it, you haven't actually mimicked gravity. You see. Anyway, I was saying, do it crudely and for the solution where you just linger around in the middle, it shouldn't change. I don't know, I'm asking.
Yeah, no, so the box must be exponentially large.
Yeah.
To get energy levels right. So e to the capital N type of box you are putting. So I don't see that intuitively. I would feel that it should be okay, and you would get very similar answer.
Sorry. Yes, I think that's fine. It's a much longer time.
Yeah. Okay, so I was just trying to tell you that suppose you only work with one coupling. you notice that this UV coupling which we had in the UV formulation of the SYK model, we got out this IR type of coupling, which is the same as the UV coupling if S1 dot S is equal to 1. That is the Kourkoulou-Maldacena case. But let's see what happens if you try to measure the original spin. Is it possible for us to recover the original microstate? That is the idea. Okay, so now again, numerical work helps you a lot. And it helps you to have an estimate of what this UV coupling would be. And I claim that it is some constant, a fixed number, which we can detail. Okay, I'm not going to do that. Importantly, which falls off as 1 upon square root of beta. Remember that red and green little plot, that sausage, with this fellow is just doing as 1 upon square root. Very small bit. Okay, so this is so I can choose this C to be some reasonable value here. Just it can be made more rigorous, but it's the UV coupling, so I have a right to what is reasonable there, and I do it in such a way that this model with these values of the coupling will land up in the red region along the line. This case G prime is 0. All right, fine. Now, hold that for a moment. Now let us consider this asymptotic solution which I was talking about before. In that phase, if I go as minus A times T, where A is some positive number related to the inverse temperature of the smaller black hole, and there's an energy which you can compute, which I showed. So this goes as the square of this thing. I mean, what I'm trying to say is that this is like an observable in the theory. Somebody can observe it, and this formula can enable you to invert G1 in terms of. So in a sense, you're measuring. There's nobody around, but assume there is some experiment. It's doing this energy because it's more physical. You can measure it. So you can compute this G1 square. Once you compute this G1 square, and you use this UVIR formula, then you can have a formula for S1 dot S square given by. So this right hand side is known. That's what I'm saying. So if you repeat this process, means it's one run is done. Now go and do it for different values. Different values of the spin S1. So this is when I was slightly lost. You started the state corresponding to spin S, was it? The micro, you don't know that. That's the point. You don't know that? You don't know that. But I know S1 because I am putting it. And how was S1 put in? You finally had this state there? This one was put in the coupling. Oh, in the coupling. In the coupling. Okay. Now I got. So S1 dot here all. I understand. And then sorry, just so I make sure, then you look at how much energy was retained, say, in the black hole, which depends on this law. So, if G prime is there, also there's a similar formula, slightly different. There's a G prime square times the black hole temperature. Yeah, I'm not saying all that. It's complicated. So now, so you have this equation. I know I've introduced this alpha for so many times I will now run the system. The question is how many times I have to run it to be able to tell you what the initial state is. So you have this type of simple equation, right? See, the effective theory always talks about squares. So you have this type. Now this is some matrix form. So we want to invert this equation for SKSL. But firstly, you notice that because SK square is 1, this object, all these fellows SKSL, there are only so many independent champs. N upon 4 times 2 minus 1. That's obvious. So therefore, this alpha has to also be so many up to N upon 4 is of order n square. So then, if I perform so many experiments, then I can really invert this equation and tell you what the initial value of S is up to a sign. Cannot fix the sign this way. So in fact, so this is in the open quantum system of the SYK model, which the path is also there. It's not that everything is evaporated and you're just looking at the bath problem. That's a much more complicated problem. Right. How to recover information. Yeah, please.
Sorry, Spenta. So basically, if I understand, your spins span the entire 2 to the n over 2 space, the choices. And just so I put everything in, how many measurements for it? It was not order
n squared.
So it's not order 2. No, much less.
It's not of the order of the dimension of the Hilbert space. That's the point. And it's explicit. So, I mean, there's no, for that there is no discussion.
And isn't that a surprise?
No, it is not, because it's a different problem than what you're used to working on. You're used to working on a much more complicated problem that the black hole is evaporating. Okay, from the radiation, how do you reconstruct the state of black hole? That's not the problem.
But couldn't the black hole, again, couldn't it have evolved to any one? Because the SK is, so probably it's evolution, the states are special, that it's evolution. Only samples much smaller.
Yeah, and linear combinations of these.
Then states of the original
originals.
Then
you would have got much.
Oh, so that's, but you know, I want to start with one black and discuss it. So what would that mean? What is that? What?
No, he's saying that, you know, how about a linear combination?
But what is the meaning of that? What? See, because many things here. So you take this type of state, then you can prove that all these flip invariant operators at large n cannot actually see the initial microstate at all. Now, if you do what you are saying, then what about all those coefficients set? So, how much information would you like me to? But what I do not understand is the interpretation of the state you are. I understand what you're saying. A linear combination of these.
Then you get the 2 to the n. Then you got the whole thing.
Because then everything is.
You're just serving one basis element direction. You know you're on a basis. And that to a direct product.
That's simple, right?
Yeah, okay, I understand. Okay, no, just because from the black hole evaporation point of view, we might like to ask a question like you have a black hole which starts off with some entropy and then it evaporates, it's still left over, and it has some net entropy. How hard is it to figure out roughly? If you had started with one of the original states, which one? Right, that's the analog question, right? And then I might have thought that it's at least as hard as the entropy of the leftover pack. I mean, that's what you would expect, right? But here, I mean, she's correct me, but it seems it's much easier.
Somehow it's become classical. Because if the states are parameterized by this spin in each unit.
Right.
And then the information is just about the classical orders. So yeah, somehow become very small.
It's not true to the ends.
Yeah.
You're not cited an operation. Whatever time you have, remember you say all the times same time. In some sense, they are to recall this evaluates because they are allowing themselves to decide on
I mean, still, you're not doing some local measurement.
because they're changing. That's what you're saying.
Also, some specifically, I do not know how to compute the state you are proposing because I do know the matrix elements in spin 1, spin 2 of these operators, which I don't know. I remarked that I needed the diagonal part for the hand. And that was enough because that represents a line. That's the microstate of a line.
Yeah, in fact, it's probably a little stronger. If you take linear combinations, then it's not clear whether it corresponds to microstate, because all those theorems which were proved by Maldacena are about this particular basis of microstates, which look like solvers. If you take a linear combination of them, many of these things will not work.
So my point is, it is not a model of a black hole microstate. It's
Randoms. You take randoms to create microstates. Yes, random function. There are also random.
So that the off diagonals are all 0.
Sorry.
So that the off diagonals are all 0.
So Gaussian random.
then more or less you get
I
better.
expected that.
You're right. I agree. But just with just arbitrary coefficients, it's
If you take one, let's 1 plus square root of 2 times 1 microstate plus another microstate.
Okay,
That does not look like a
I'm talking about randoms.
randoms. Okay, that,
okay. I should continue with those things. And of course, my apologies. Doesn't matter.
all right.
No, hugely close. Hugely close. So, this is a simple way of explaining. Now you can apply it to our whole sausage diagram of the regions. And you can arrive at a very similar reasoning. And in fact, even the degeneracy of the spin, whether the spins are, I give you a set of spins and the name. What I discussed with you cannot distinguish between plus and minus spins. Really, effective theory is constructed. But here, you can also do that. Very simple way. So this is the actual calculation. Given the so you have two solutions in the actual calculation. One is the black hole phase, in which you have a formula like this, and again you do whatever I have discussed. You get to initial state up to a sign. SKs all minuses. Now to distinguish between them, what you do is the following. You realize that this coupling distinguishes between whether S1.S is +1 or S1.S is minus. And so you do two experiments, this one and with this one. And that will correspond to two different asymptotic solutions correspond to GG prime and minus G prime. And both cannot be in the green group. Because as I told you, G going to minus G is not a symmetry of that diagram. You also have to take G prime. So in this way, you can sort of distinguish between whether it's the plus sign or the minus. This can be done some very clearly. So what I would like is to have some response to this part of the talk.
Just to understand, your original states were parameterized by plus by 2 to the n. There were 2 to the n possible original states, right? Then that's correct, right? Yes. But how can you then use n squared pieces of data to say which one of 2 to the n?
Yes, that's what I was asking. So shall I explain again? Maybe.
Some restricted set, right? That's what is.
But still, there are 2 to the n possible numbers, right? Yeah, but a lot of the experiments, you would have thought naively that you need 2 to the power n by 2 experiments.
Yeah.
So, but many of these things will be redundant because once you have done with 2, you can construct a plane using that 2, and you can discard all possible other experiments.